Okay, hello everyone. So last time we used the expected values or first moments to prove bounds or to derive bounds on independence numbers, if you remember. And we did that, by using expected values or first moments combined with alterations, meaning that we use probabilistic method to prove existence of a structure similar to what we are looking for. And then we modified or altered that structure to get the structure that we are looking for. Okay, so today we want to continue that topic. So today, still use expected values and iteration method. Basically, now how do we want to use, or in which direction do we want to use them today? Basically, high girth and high chromatic numbers. Okay, let me explain what this topic means. Okay, so first we need to know the definition of girth and chromatic number for a graph. So definition for a graph G, the girth of G denoted by G of G is the length of the shortest cycle in G. So for example, let's say, I always like to give simple examples, after to understand definitions or theorems. So let's say we have a graph like this. Let's say, what is the shortest cycle in this graph? So in this graph, basically G of G is equal to 3. Okay, the shortest cycle is this triangle that we have here. Now another definition is chromatic number for a graph G. The chromatic number of G denoted by chi of G is the smallest number of colors, the smallest number K, such that G has a proper K coloring. So what is proper K coloring? Proper K coloring of G is a map C from vertices of G to 1 to K, such that C C of U is not equal to C of V for any edge U and V inside the set of edges of G. Okay, let me explain this. Girth was simple, concept. You just need to find the shortest cycle, and the length of shortest cycle is called girth of a graph. But what about chromatic number? To understand chromatic number, first we need to understand the concept of proper K-coloring of a graph G. Now, K-coloring of a graph G means that we want to color vertices of G. Okay, so remember this time, previously we were looking at cases where we looked at the coloring of edges of a graph. Okay, so this time we are looking at coloring of vertices of a graph, okay, such that any edge that you consider in your graph, the endpoints of that edge, the two vertices that which are endpoints of your edge, have different colors. Okay, so if you can color your graph in this way, color the vertices in this way, this is with K colors, that is called a proper K coloring. Now, the minimum number of colors that I need in order to have a proper K coloring of a graph is going to be called the chromatic number. Of course, it's obvious that, in the worst case, I mean, if you want to do it trivially, basically, you can color each vertex with a separate color. Let's say if you have 20 vertices, you can use 20 different colors, one for each vertex, and of course, then you would have a proper K coloring, because for each vertex, you're using a different color. So of course, in that case, any edge that you consider, the endpoints have different, the vertices at the endpoints have different colors, okay? But we don't want that. We want to use as minimum number as colors that we want in order to have a proper K coloring. Okay, so let's look at an example. Okay, let me charge my pencil. So example, let's say we have say this tree. These are the vertices. Okay, so how many colors do I need at the minimum to color the vertices such that any edge that I consider the endpoints have different colors? So what do you think, how many colors, the minimum, do we need? We only need 2 colors in this case. So this I can use, let's say, red, and this one blue, and this one red, and red, and this one blue, and this one again red and red. See? So this is a 2 coloring of G. So that means chi of G is 2. Of course, I cannot use 1 color, and therefore, but I can have a proper 2 coloring, because any edge that I consider here, let's say this edge, for example, one endpoint is blue, one endpoint is red, or this edge, one endpoint is blue, one endpoint is red. Same thing for this edge and this edge. To have a 2 coloring of G, and chromatic number of this graph is G. So see, the same idea. So why was I able to color this with only 2 colors? Because there was no cycle, right? So in other words, if you have a tree which has no cycle, then you can only use 2 colors. 2 colors would be enough. Just do it alternately, right? So again, if this continues from this side, again, you know, the next branch would be blue and then red and then blue. Same thing for here, okay? So one remark is that if a graph G contains no cycles, and no cycles, then the chromatic number of G is equal to 2. Okay, now the question here is, if G contains no short cycles, can we say chromatic number of G is small? See, we just said if G has no cycle at all, then the chromatic number is only 2. Now, what about if I say, for example, the G has no short cycle? So, for example, it has no triangle or no square. So, if I basically weaken the assumption a little, instead of no cycle at all, no short cycle. Can I say that the chromatic number, well, it can't be 2, as small as 2, but can I say still is small? In other words, if I weaken the condition of this remark a little, can I say the remark still holds with a weakened conclusion as well? So this is the question. And this question was answered by Erdos, and the answer is no. So theorem, given any integers k and l positive, there exists a graph G such that a girth of G is bigger than L and chromatic number of G is bigger than K. So for example, if you set L to be 4, okay, let me explain this theorem to you. Let's say if you set L to be 4. So that means you want the girth of your graph to be bigger than 4. Bigger than 4 means it contains no cycle of length 3 or 4. The shortest cycle will have length bigger than 4. So in other words, your graph will contain no short cycle of length 3 or 4. Then can I say that, because of this, if you think about this question, can I say that the chromatic number will be small? Again, remember, I'm talking about the weakened version of this remark, meaning that I'm weakening the condition. Can I also say that remark still holds with a weakened conclusion? The answer is no, because if you set L to be 4, you're allowed to set K to be any number, let's say 1000. So there exists a graph where the chromatic number is bigger than 1000, meaning that you need 1000 different colors to color, to have a proper K coloring of that graph, you need at least more than 1,000 colors. But the shortest cycle in that graph is of length more than 4, meaning that that graph has no cycle of length 3 or 4, has no short cycle, but still the chromatic number is very large. Okay, so this theorem is proved by Arthur. So it means that, in other words, so remember the topic of this lecture was high girth and high chromatic number. So the question is, if I know that the graph is high girth, can I conclude that it has low chromatic number? The answer is no. This theorem proved by Erdős says that you can have a graph which has high girth and also high chromatic number. Okay. All right, so let's see how we can prove this theorem. Proof. Going to charge there, and so. Okay, we consider a random graph G equals G of N and P. Okay, so again, in most theorems we have proved in this course so far, we are looking for existence of a graph with certain properties, and we're going to consider random graphs if we show that the graph that we are looking with the properties that we're looking for exists with positive probability, then it shows the existence of such graph. The only, maybe the only exception was what we proved last time, where we proved that the graph was fixed and given, and we wanted to prove a property about it. So instead of considering random graphs, we consider random subset of vertices of G. But this time again, it's similar to the theorems we proved before, which is to prove existence of a graph G with certain properties. So we are going to consider random graph G with parameters N and P. So what does this notation mean? i.e. a graph with N vertices. So this, first of all, it means it has N vertices. Where each of N choose 2 edges appear independent of each other and with probability P. So when we say G of N and P, means first of all, we are going to consider a graph with N vertices. So that's for sure. Now, if you have N vertices, you can potentially have N choose 2 edges, in which case you will have a complete graph of size N or Kn. But each of those edges appear in this graph with probability P and independent of other edges. So first edge appears with probability P, second edge independent of first edge, and again appears probability P, all the way to the last edge, which is the N choose 2 edge number N choose 2 again appears with probability P and independent of other edges. Okay, so still here, I haven't told you what n is and what p is. Okay, so n and p to be chosen later. Okay, now I want to count a number of cycles of length at most L. Okay, so remember that L is a given number. L and K were given in the beginning. I want to find a graph. K and L were given. I want to find a graph with girth bigger than L and chromatic number bigger than K. So I want to count the number of cycles of at most L in G. So let X denote the number of cycles of length at most L in G. Okay, so basically X is a random variable. Now, what type of random variable is it? So to understand X better, I want to simplify this and write this random variable as sum of other random variables. Okay, so we can write X as follows. So I can write X, let's say X equals X, let me say 3 plus X4 all the way to XL, where X3 measures cycles of length 3. X4 measures number of cycles, number of cycles of length 4, and all the way to XL, which measures number of cycles of length L. So if I want to count number of cycles of length at most L, I have to first count number of cycles of length 3, then length 4, and all the way to length L. Okay. Now I want to find expected value of X, because remember we are using the still first moment technique. So hence expected value of X is equal to expected value of X3 plus expected value of X4 all the way to expected value of XL. Now, what is the expected value of X3? X3 counts number of cycles of length 3. Okay, so how many cycles can I have of length 3? Right? Well, depending on the type of graph, now if G, remember G is a random graph, but like in the most extreme case, if G is a complete graph, then I have the largest possible number of cycles of length 3, right? So if G is a complete graph, so I want to use this fact. See, note, if G is, let's say Kn, then number of cycles of length I is 1/2 times I minus 1 factorial times n choose I. So this is a standard graph theory problem. You can check it yourself as an exercise that there are this many cycles of length I in a graph, in a complete graph of order n. Okay, so again, now let's think about x3. x3 is the counts the number of cycles of length 3. Now, what are the possible outcomes of x3? I can have 0 cycles of length 3 or 1 cycle of length 3, okay? But the most case, so x can be x3 can be either 0 or 1 or 2. But in the case that g is kn, this is the maximum number, right? In kn, this is the number of cycles of length I. So in G, there's a random graph. This number is the maximum number that I can have. So the outputs of x3 can be either 0 or 1 or 2, all the way to 1/2 times 3 minus 1 factorial times n choose 3. Okay, what type of random variable do you think x3 is? See, x3 is a binomial random variable. Why? Because we have like this many random trials, right? So, and I can have either 0 success in them. So success means 0 of these many, I have this many total possible 3 cycles. I can have 0 of them appeared in my graph or 1 of them appeared in my graph. So I can have 0 success or 1 success or 2 successes. And if all of them are appearing, that means I have all successes in all trials. Okay, so what is the probability of success here? So in each trial, so if I call them, you know, for example, 3 cycle number 1, 3 cycle number 2, to 3 cycle number, this number, in the first trial, I can have success. It would be success if that 3 cycle is appeared. What is the probability of it? Well, the first 3 cycle, basically it's a triangle, right? So each edge in that triangle is appeared in my graph with probability P. I'm talking about my random graph is G of N and P. So the first, so if the G of N and P, so each edge is appeared with probability P. So in the triangle, because it has 3 edges, each of the 3 edges appear with probability P. They're independent of each other. So the first triangle appears with probability P to power 3. Second, so that's the probability of success for the first trial. Again, for the second trial, which means whether the second trial appeared or no, again, the probability is P to power 3. So each trial has probability of success P to power 3. And there are this many trials in total. So I have a binomial random variable with parameters. So note x3 is a binomial random variable with parameters n is this number, this many trials, and probability of success is P to power 3. So that means expected value of x3. Well, we know how to find the expected value of a binomial random variable. Just multiply the probability by number of trials. So this is going to be 1/2 3 minus 1 factorial and choose 3 times P to power 3. Okay. Similarly, expected value of x4 is 1/2 4 minus 1 factorial and choose 4 P to power 4. And expected value of XL is 1/2 L minus 1 factorial and choose L p to power L. Therefore, expected value of x is equal to sum of these numbers. So it's going to be 1/2 3 minus 1 factorial and choose 3 p to power 3 all the way to 1/2 L minus 1 factorial and choose L p to power L. Okay, now I want to simplify this expression, some algebraic manipulations. So note 1/2 I minus 1 factorial and choose I. Let me simplify this a little. 1/2 I minus 1 factorial n factorial over I factorial n minus I factorial. So I factorial and I minus 1 factorial, they simplify with each other. So it's going to be 1/2 n factorial over n minus I factorial will be n times n minus 1 all the way to the n minus I plus 1 divided by I, because I minus 1 factorial over I factorial is 1 over I, and this is less than or equal to n times n minus 1 n minus I plus 1, right? If the denominator is 2I, so if I get rid of it, I get a number which is bigger than the original number. And this number is less than equal to n times n times n, I times, and this is n to power I. So this number that I have here is less than equal to n to power I. And therefore, if I plug this back into this expression, what can I say? Thus, expected value of x is less than or equal to, see, this number here is less than equal to n to power 3, all the way to this number is less than equal to n to power L. So this is less than equal to n to power 3 p cubed plus all the way to n to power L p to power L. So basically this is sum I from 3, or let me write it, I mean you can write in terms of sigma notation, or not using that. I can also write this as np to power 3 all the way to np to power L. Okay. All right. So now, remember we said that we are going to choose n and p later. So I haven't said anything about n and p yet, but as we go through the proof, we are going to see some conditions that we have to impose on n and p one by one. Okay, so I'm going to mention those conditions. So we will impose conditions on n and p. So the first condition is choose, let's say, p to be n to power, let's say, 1 minus epsilon, with some epsilon, small number epsilon. I'm going to specify epsilon as well. So, but if I do that, why do I want to do this? Because in this case, n times p will be how much? So, or let me say, because I want n times p, so epsilon minus 1. So then n times p will be n times epsilon minus 1, and this is n to power epsilon. Okay, and then I have n eps, so this is going to be then expected value of x will be less than or equal to np's n to power epsilon, so n to power epsilon to power 3 all the way to n to power epsilon to power L. Now epsilon is a positive number, I haven't specified it yet, but I can say that this is less than or equal to n to power L epsilon all the way to n to power L epsilon, which is less than or equal to L times n to power L epsilon. Okay, so how should I choose? What other condition should I impose on n or epsilon? Epsilon hasn't specified yet, but now so the second condition that I want to impose is that choose epsilon to be, let's say, 1 over 2L. And the other condition is choose n such that L is less than root n over 4, okay? So remember that L is a fixed number given to us from the beginning. So of course, I can choose n as large as I want. So of course, you can choose a number n big enough so that root n over 4 is still bigger than the given number L, okay? So under these extra restrictions on epsilon and n, then we can simplify expected value of x as, so then expected value of x will be less than root n over 4 times L is less than root n over 4 times n to power L epsilon. So n to power L epsilon is 1 over 2L. And this is also root n, so this is going to be n to power 4, n over 4. Okay, why did I want expected value of x to be less than n over 4? Because then I can apply Markov inequality, okay? So Markov inequality, next, apply Markov inequality. What was Markov inequality? Which was saying that p of x bigger than equal to a is less than or equal to e of x over a. Of course, if x is a non-negative random variable. So then I can say that p of x bigger than or equal to n over 2 is less than equal to e of x over n over 2. E of x is less than n over 4 over n over 2. This is 1/2. Okay, so what can I say then? Well, remember that, most of the cases that we have done so far, we had probability of something bigger than 0. Now, in this case, what can I say? This is a little bit different than from other theorems or other techniques that we have done. So this time is less than 1/2 this probability. So this means probability of x being less than n/2 is bigger than or equal to 1/2. Okay, so now we have probability that x is less than n/2, bigger than or equal to 1/2. Well, X was the number of short cycles, basically, right? So the cycles of length at most L. But I want to have no short cycle because I want the length of shortest cycle to be bigger than L. Remember what we're trying to prove here? I want the length of G of G bigger than L means the length of shortest cycles I want to be bigger than L. So which means I don't want to have any short cycle. Well, right now I concluded that number of short cycle is not 0, which is what I want, but is less than n-half, and which means a small number of them. So I'm going to, again, you'll see that I'm going to delete one vertex from each of these cycles to ruin all such cycles, and I'll get a graph which has no short cycle anymore. So we're going to alter it. But one thing that you're wondering probably now is that, well, if I want to say there exists at least one graph with small number of short cycle, usually we had probability of such thing greater than 0. Why do I need greater than 1/2? So this is the difference between this theorem, proof of this theorem, the idea, and the previous theorems. Because having no short cycle is not enough for me. I want to have two conditions satisfied. Again, let's look at the theorem. I want to have two conditions satisfied, G of G bigger than L and chi of G bigger than K. So if I needed one condition, yes, probability greater than 0 is enough. But two conditions, if I can say for each of these conditions, probability is bigger than or equal to 1/2, then they must overlap with each other. And then I can say that there exists a graph that has both of those conditions. Okay, now regarding the chromatic number, So the idea here is to relate this with independence number. We'll show that alpha of G is less than some number A for a graph G and a proper number A. Okay, so how do you think this is related to the chromatic number? If I show that the independence number is less than A, what does this imply about chromatic number? So if, let's say for example, what is the question is, what is the connection with the chromatic number of G? Okay, so the connection is number of vertices in G is less than or equal to A minus 1 times chi of G. Okay, let me explain this. Well, we know that we can use chi of G number of colors to color the vertices so that any edge that I consider, the endpoints of edge have different colors. Okay, now let me consider, let's say, one of these chi of G colors. Let's say color number 1. Now for color number 1, I cannot have more than A minus 1 vertices of this color. Why? Because if not, I will have A vertices of color number 1, but I am not allowed to draw any edge between these A vertices, because if I draw even one edge between any two of these A vertices, I'm going to have an edge whose endpoints are same color, color number 1, and that is not allowed. So color number 1, we can color at most a minus 1 vertices of color number 1. Again, at most a minus 1 vertices of color number 2, all the way to at most a minus 1 vertices of color number chi of g. So each of these colors is going to be used for at most a minus 1 vertices. Therefore, the total number of vertices of the graph is going to be less than or equal to a minus 1 times chi of g. Okay, so this means, so let me explain this briefly. Each color can be used for at most a minus 1 vertices. Otherwise, we would have an independent set of size A, of size at least A. Okay, this is a brief explanation. Now, thus, chi of G is going to be bigger than or equal to V of G divided by A minus 1. Okay, okay, so now if, so remains to choose, or let me say to ensure V of G, ensure V, the number of vertices of G and A are chosen properly so that chi of G is bigger than K, which is what we need in the theorem. Okay. So also remains to show alpha of G is less than A, and we have to also choose A properly. Okay. So back to showing alpha of G is bigger than A. Showing there exists G such that alpha of G is, sorry, less than A, less than A. Okay, so probability that alpha of G is bigger than or equal to A is equal to, well, when can I say that alpha of G is bigger than or equal to A? If I have an independent set of size A, then that means that the independence number will be at least A, and possibly bigger than A. So this is same as probability of having an independent set of size A. Now, how can I make sure that I have an independent set of size A? So first of all, I have to choose A vertices out of N vertices, and which are going to be my independent set. So between any two of these A vertices, I'm not allowed to have any edge. So I will not have an edge with probability 1 minus P, remember? So 1 minus P to the power of number of edges between, potential edges between these A vertices, which I am requiring none of them to exist. So 1 minus P to power A choose 2 times P to power, so the remaining should have edges. So P to power N choose 2 is the total minus A choose 2. So for any fixed A vertices, the probability is 1 minus p to the power a choose 2 because I'm not allowed to have vertices between those edges between those vertices, any two of those A vertices, and I need to have edges between other vertices, which is n choose 2 minus a choose 2, each one with probability p. Now this is for any fixed set of A vertices. I have n choose a options to choose my A vertices. This is the probability of having an independent set of size exactly A. And then this is obviously less than or equal to n choose A, 1 minus p to the power a choose 2. Okay, now this one is going to be less than or equal to n to the power a times e to the power minus p to the power a choose 2. So let me also justify this. So n choose a is n factorial over a factorial, n minus a factorial, which is n times n minus 1, a plus 1 to over a factorial. And then this is less than or equal to n times n times n, which is n to the power a. So this was easy. And also, we know that 1 plus x is less than or equal to e to the power x. Okay, so this implies that, well, this inequality here, we have n to the power a, e to the power minus p to the power a choose 2. So this becomes n to the power a times e to the power minus p times a minus 1 over 2. Now, if we simplify this, I can write n to the power a as e to the power a ln n, right? So a ln n minus a p times a minus 1 over 2. Now I can write this as e to the power a times ln n minus p times a minus 1 over 2. Okay, so now I want this. Okay, what was this? This was probability alpha of g bigger than or equal to a. So I want this one to be less than 1/2 so that probability of alpha g less than a is bigger than or equal to 1/2. Okay, so how can I choose this a that ensures that this is going to be less than 1/2 for appropriate n and a. So if this, well, a is, assuming I want to choose a positive, and I have to choose a positive, you know, p of alpha g bigger than or equal to a, we are talking about such probability. So a is positive integer. And so how can I make sure that this number is going to be less than 1/2 if I can make sure that this expression inside the bracket is negative? Then ultimately this can become arbitrarily small. So I want to choose a such that ln n minus p times a minus 1 over 2 is less than 0. And this means we want p times a minus 1 over 2 to be bigger than ln n. That means a minus 1 should be bigger than 2 ln n over p. And a should be bigger than 2 ln n over p plus 1. So we just need a number bigger than 2 ln n over p plus 1, say So choose A to be, let's say, 3 ln n over p, the ceiling of it, just to be safe, and a number which is bigger than 2 ln n over p plus 1 and is also an integer. So once we choose A to be this number, then this expression inside the bracket will be negative. So we are going to get e to power ln n over p times the negative number, which the power goes to minus infinity as n goes to infinity. So the whole number goes to 0, right? So let me call this expression, let's say, you can call it star, this expression here, and then I can say that as n goes to infinity, this goes to 0. I just want to call it star. So with this choice of A, star goes to 0 as n goes to infinity. So for a large enough n, let's say we have p of alpha of g bigger than or equal to a, less than, let's say, 1 over 4, because this expression goes to 0, so I can make sure that if n is large enough, it's going to be less than any positive number that I want. So let's say less than 1 over 4, even less than 1/2 would work okay, but just to be safe, let's say less than 1 over 4. And then this means p of alpha of g less than a is bigger than or equal to 3 over 4. Okay. All right, so what have we shown so far? So far we showed p of alpha of g less than a is bigger than or equal to 3 over 4, and p of x less than n over 2. This is also bigger than or equal to 1/2. If you remember, we showed this inequality about p of x here. X less than n/2 bigger than or equal to 1/2. And x was measuring the, it's a random variable counting the number of cycles of length at most L. All right. So we have these two. So now I want to say that there must be a graph that satisfies both of them. So for each of them, if I want a graph satisfying just one of them, well, probability bigger than 0 is enough. But if I want a graph that satisfies both conditions at the same time, this condition would be enough. I told you the intuitive reason behind it, that, you know, they must overlap because each of them are valid for at least 50%, if you remember. But I can also prove it using probability axioms. So I can also say that, yeah, axioms and properties of probabilities. So thus there exists a graph G such that x is less than n/2 for G, and alpha of G is less than A. Why is this? Because if you want P of A intersection B, what is this? This is P of A plus P of B minus P of A union B. So if this is bigger than or equal to 1/2, let's say if one of these you call it event A, the other one you call it event B. So this is bigger than or equal to 1/2 plus 3/4. And this one is at most 1. So this is bigger than 0. Okay. Okay, now we have a graph now that has x less than n/2, meaning that number of cycles of at most length at most L is less than n/2 and has independence number less than A. Now let's start with x less than n/2. We know that the number of cycles of length at most L is less than n/2. Now what do I need? I need to have g of g to be bigger than L, the girth, which means that I want the shortest cycle to have length at bigger than L. So basically I have to ruin every cycle that has length at most L so that I have no cycle of length at most L anymore, and therefore I would have the length of shortest cycle to be bigger than L. Now, how can I ruin the cycles? We did this technique before. I just need to delete one vertex from each of these cycles. Okay, so now, and by the way, G, remember we were considering G of N and P. So all the graphs that we're talking about has N vertices, right? So G has N vertices in total. Now, if I remove one vertex from each of these cycles of length at most L, I would still have at least n/2 vertices, right? Because the number of cycles of length at most L is less than n/2. So now delete one vertex from each of cycles of at most of length at most L in G above. Then we get a graph, let's say G star, that contains no cycle of length at most L, which means the girth of G star will be bigger than L, the length of shortest cycle. And what about the independence number? Independence number means the set, the size of largest independent set. In the original graph was less than A, right? Now I have deleted some vertices from that graph. So the size of largest independent set cannot become bigger than the original one. It can only become possibly smaller. So if the original graph has independence number less than A, this one also still has independence number less than A. This is less than or equal to alpha of the original graph G, which is less than A. Okay, so, and remember that I already have one condition that I needed. The girth number is bigger than L. The other condition was chromatic number should be bigger than, I think K, call it K. Chromatic number should be bigger than K. Now, we said that we are going to connect chromatic number with independence number. What was the connection? We already established it. See here. chi of g is bigger than or equal to number of vertices divided by a minus 1. So let me call this one 2 star. Now I'm going to apply this inequality for the new graph G star. So by 2 star above, okay, so chi of G star will be bigger than or equal to number of vertices in G star divided by a minus 1. Number of vertices bigger than or equal to n over 2. A was ceiling of 3 ln n minus 3 ln n over p. So a minus 1 will be less than or equal to 3 ln n over p, and therefore, because it's in denominator, I can say that this fraction is bigger than or equal to n over 2 over 3 ln n over p, which is np over 6 ln n. NP, by the way, what was NP? Do you remember? Let me show you in the beginning. We established how we should choose P. Here. NP was n to power epsilon, and epsilon was 1 over 2L. So NP is n to power 1 over 2L. NP is n to power 1 over 2L. Divided by 6 ln n. And this number goes to infinity as n goes to infinity. So if n is large enough, I can ensure that the right-hand side is bigger than k, which is exactly what I'm looking for. So since n to power 1 over 2L divided by 6 ln n goes to infinity as n goes to infinity, for large enough n, we have n to power 1 over 2L divided by n to power 1 over 2L divided by 6 ln n bigger than k, and hence G star, this choice of parameters would be the graph satisfying G of G star bigger than L and chi of G star bigger than K. Okay, so we wanted to show, let me summarize, we wanted to show that we can have a graph with a high girth and high chromatic number, meaning that any K and L that are given, we can choose a graph that has girth bigger than L, chromatic number bigger than K. So we used, again, a common technique in this course, which was considering random graphs, G of n and p, meaning a random graph with n vertices, and parameter p, meaning that each edge is present with probability p and independent of other edges. And we assume that like x, the random variable x, is the number of cycles of length at most L. We showed that probability that x is less than n half is less than 1/2 for appropriate choice of n and p, of course. Then we showed that probability that alpha of g is less than a, that's also less than, so p of x less than n half was bigger than equal to 1/2. P of alpha of G less than A is bigger than or equal to, we said 3/4. And then we said that therefore there must be a graph that satisfies both of them because they must overlap. So if you need only one condition, we can say probability is greater than 0, therefore the graph exists. If you need two conditions or more, we can say that, you know, P of one of them bigger than or equal to 1/2, one of them, let's say, bigger than 3/4. And mathematically, I also established that then P of A intersection B has to be bigger than 0, meaning that there must exist a graph satisfying both conditions at the same time. And once I established that, then we altered the resulting graph. Because I'm looking for a graph that has no cycle of length at most L. Right now, my graph, which I call it G star, had the property that it had length, cycles of length at most L, but at most N/2 of them. So once I delete one vertex from each of those cycles, I'm basically ruining all of those cycles, and I would still have a graph with still at least N/2 vertices, which now has no cycle of length at most L, so it has girth bigger than L, which is exactly what I want. And what else? And the other condition was the chromatic number to be bigger than K, where chromatic number bigger than K, we already established that for G star, the independence number is less than A, but we established a connection between these two. And that is chromatic number is bigger than or equal to number of vertices divided by A minus A, where A is the upper bound for independence number. So we used that, we calculated this lower bound for chromatic number. We plugged back, you know, the value of A here, and then we saw that, you know, we get an expression that goes to infinity as n goes to infinity. Therefore, we said for large enough n, this lower bound will be also bigger than K, which is exactly what we need. Okay, so yeah, we established this result about girth number and chromatic number. Of course, you know, there could be lots of applications for these concepts in mathematics, in computer science, in daily life. You know, for example, chromatic number, at least how many colors do we need to color the vertices so that any edge that we consider the endpoints have different colors. So for example, we can consider the vertices to be classes in university. For example, I don't know, math 100 or math 200. And then we can connect an edge between them if those classes have a common student, let's say. And let's say you want to schedule the lectures or schedule the final exams. So let's say if you want to schedule the final exams, you cannot schedule in a way that a student you put two different classes at the same time slot with a common student. You cannot do that because a student which is registered in math 100 and also math 200, or for example math 200 and biology 200, cannot write the exam at the same time. So if assigned, for example, considering different time slots is same as coloring the vertices. So if you colored for example, blue color could be Friday morning, red color could be Friday evening. So you cannot have two edges with the same color which has an edge between them, because then that means you have the time slot of two courses are same and those two courses have a common student, which is not what you want. So finding the minimum number of colors that we need means finding the minimum number of time slots that we need for scheduling, let's say the final exam or the classes or the lectures. Okay, this was a simple example of chromatic number, but of course there are so many more applications. But yeah, so we use the probabilistic method to prove this interesting result, which was done by Erdős, this proof, as I said before. Okay, so thank you. And next time we will look at the second moment method and how to use it to prove results. Okay, thank you and see you.